In 2024, physicists in Italy did something that should terrify you. They built a tiny universe inside a laboratory, a pocket of reality held together by lasers and magnetic fields, cooled to less than a millionth of a degree above absolute zero. And then they watched it destroy itself. A bubble formed inside the system, a sphere of true nothingness that expanded outward, rewriting the laws of physics inside it, erasing everything it touched. It was the first time anyone had ever observed false vacuum decay, the mechanism by which empty space itself can collapse. Not a simulation, not a computer model, a real physical process, observed in a real laboratory, confirming a prediction that has haunted physicists for decades. The prediction that the vacuum beneath your feet, the emptiness between the atoms in your body, might not be stable, that it is balanced on a ledge, and that at any moment, without warning, a bubble of true vacuum could appear anywhere in the universe and expand at the speed of light, destroying everything, not just matter, the laws of physics themselves. You would not see it coming. You would not feel it. You would simply stop existing. And that is only the first theory we are going to explore tonight. If you enjoy our calm nighttime journeys, remember to like and subscribe. We highly encourage our community to discuss the video topics in the comments and react to other comments. It is the most fun when we share our thoughts. Now, let us begin. Tonight we are going somewhere dangerous, not to a black hole, not to the surface of a dying star, somewhere closer, somewhere you have never thought to be afraid of. We are going into the empty space between the atoms in your hand. Because there is a theory in physics right now, supported by real mathematics, confirmed by measurements at the largest particle accelerator ever built, that says the vacuum beneath your feet is not stable, that the emptiness holding your atoms together is balanced on a ledge, and that at any moment, without warning, without cause, without so much as a whisper, a bubble of true nothingness could appear somewhere in the universe and erase everything, not just life, not just matter, the laws of physics themselves, replaced, rewritten, gone. And in 2024, for the first time in history, scientists watched it happen in a laboratory. Not in our vacuum, in an analog, a rehearsal, but a rehearsal that proved the mechanism is real. We are also going to meet the most terrifying form of matter ever theorized. A substance so stable, so perfect, that if a single microscopic droplet of it touched ordinary matter, it would convert everything it touched into more of itself. Your hand, the floor, the planet. And then we are going to look up into the silence of the cosmos, and we are going to ask why, in a universe with 2 trillion galaxies and hundreds of billions of stars in each one, nobody has ever said hello. The answer might be that nobody survived long enough to try. The answer might be that something is hunting, and the answer might be that every civilization that ever existed made the same mistake we are making right now. Tonight we descend through the most disturbing theories in modern science. Theories that attack the ground beneath your feet, the silence above your head, and the mind behind your eyes. And by the end, you will have to decide whether the terror is a warning or a gift. Chapter 1. The loaded gun beneath your feet. You are sitting somewhere right now. A bed, a couch, a chair. The surface beneath you feels solid. The air around you feels calm. The laws of physics that hold your body together feel permanent. They have worked every second of every day for as long as you have been alive, and for 13.8 billion years before that. You have never had reason to question them. You trust gravity. You trust that oxygen will keep being oxygen. You trust that the electrons orbiting the atoms in your bones will keep orbiting. And that trust is so deep, so fundamental, that you have probably never even noticed it. It is the most invisible assumption you carry. The ground is stable. But in 1979, a physicist named Sidney Coleman asked a question that nobody wanted to hear. What if the ground is not stable? What if the empty space that fills the universe, the vacuum, the nothing between particles, is not actually sitting at its lowest possible energy? What if it is perched on a ledge, a shallow dip in an energy landscape, stable enough to last billions of years but not forever? And what if somewhere beneath that ledge there is a deeper valley, a true minimum, a configuration of reality that is more stable, more fundamental, more final than anything we have ever known? Coleman called this the false vacuum, and the mathematics said it was not just possible, it was likely. Here is what you need to understand. When physicists talk about the vacuum, they are not talking about the air being sucked out of a jar. They are talking about the lowest energy state of all the quantum fields that fill the universe. These fields are everywhere. They permeate every cubic centimeter of space. One of them is the Higgs field, discovered at the European Organization for Nuclear Research, known as CERN, in 2012. The Higgs field is what gives particles their mass. Without it, electrons would be massless, protons would fly apart, chemistry would not exist, you would not exist. The Higgs field is the scaffolding of reality, and the scaffolding might be temporary. When physicists measured the mass of the Higgs boson, 125 billion electron volts, and combined it with the measured mass of the top quark, the heaviest known fundamental particle, they ran the numbers through the Standard Model of particle physics. The Standard Model is the most successful theory in the history of science. It has predicted experimental results to 12 decimal places of accuracy. And what the Standard Model says, when you feed it these measurements, is that our vacuum is metastable, not stable, not unstable, metastable. Think of a ball sitting in a small dip on the side of a hill. It looks stable, it is not rolling, but the dip is not the bottom of the hill. There is a deeper valley below. The ball is resting in a false minimum. All it needs is a nudge, or enough time for quantum randomness to do what quantum randomness does, and the ball will tunnel through the wall of the dip and roll down to the true bottom. In a survey published in March of 2025 on the Effective Altruism Forum, researchers asked experts who had published academic papers on vacuum decay how likely they thought it was that our vacuum is metastable. 85% of the respondents who had published on the topic estimated a 20 to 80% probability that vacuum decay is physically possible. These are not fringe theorists. These are the people who study this for a living. Now here is where it gets personal. If the vacuum is metastable, then at any point, at any location in the universe, a quantum fluctuation could cause a tiny region of space to tunnel from the false vacuum to the true vacuum. This process is called bubble nucleation. A sphere of true vacuum forms, and it begins to expand at the speed of light. You cannot see it coming. Light is the fastest thing in the universe, and the bubble moves at the same speed as the light that would warn you about it. The warning and the destruction are the same event. There is no signal. There is no alarm. There is no time to be afraid. One moment you are here. The next moment the laws of physics in your region of space have been rewritten. The forces that hold your atoms together find new values or vanish entirely. Chemistry ceases to function. DNA unravels, not because something broke it, because the rules that allowed it to exist have been replaced by different rules. It is not an explosion. An explosion destroys matter, but leaves physics intact. Vacuum decay destroys physics. And in January of 2024, a team of physicists in Italy, led by Alessandro Zenicini at the University of Trento, observed this process for the first time. Not in our cosmic vacuum, in an analog system. They cooled sodium atoms to less than a millionth of a degree above absolute zero, creating a ferromagnetic superfluid. They engineered a metastable state in this superfluid, a false vacuum, and they watched as bubbles of true vacuum nucleated and expanded, exactly as the theory predicted. The agreement between their observations and the mathematical predictions was remarkable. Professor Ian Moss of Newcastle University, one of the collaborators, noted that vacuum decay is thought to play a central role in the creation of space, time, and matter in the Big Bang. But until their work, there had been no experimental test. Now there is. We are no longer just theorizing about how reality could end. We have rehearsed it in a laboratory. Should you be afraid? The honest answer is complicated. The timescale for spontaneous vacuum decay in our universe, if it can happen at all, is almost certainly far longer than the current age of the cosmos. The probability of a bubble forming in any given region of space in any given year is astronomically small. You are overwhelmingly more likely to be struck by lightning while being eaten by a shark during a meteor shower. But astronomically small is not zero, and high-energy cosmic events, collisions between particles at energies we cannot reproduce on Earth, could theoretically trigger the process locally. The universe is 14 billion years old. It has another few trillion years ahead of it before the last stars die. On those timescales, even astronomically small probabilities start to matter. And there is one more detail that will keep you thinking as we move forward. In August of 2025, a team including Jenkins, Moss, and others published a paper in Physical Review, solving a problem that had plagued laboratory simulations of vacuum decay. Their cold atom experiments had been producing false bubbles at the edges of the apparatus, contaminating the results. They found a way to eliminate the edge effect, making future experiments far more precise. The science is accelerating. We are getting better at watching reality rehearse its own destruction, so the vacuum might be a loaded gun. The empty space between your atoms might be waiting to fall. And the fall, if it comes, is instant, total, and invisible. You cannot outrun it. You cannot detect it. You cannot prepare for it. But at least with vacuum decay, the threat comes from nothing, from emptiness, from the void between particles. Surely the particles themselves are safe. Surely the matter you are made of, the protons and neutrons and electrons that have existed since the first minutes after the Big Bang, is permanent. Surely steel is steel. Surely oxygen is oxygen. But what if there is a form of matter so stable, so energetically perfect, that everything you are made of is just a less efficient version of it? And what if all your matter needs to become that perfect, terrifying substance is a single touch? Chapter 2. The Zombie Plague for Atoms. Deep inside a dead star, in a place where gravity has crushed matter beyond anything you have ever imagined, something strange is happening to the building blocks of reality. You know that atoms are made of protons and neutrons, and that protons and neutrons are made of smaller particles called quarks. Ordinary matter, everything you have ever touched, is built from two types of quarks, up quarks and down quarks. That is it. Two flavors, assembled in different combinations, producing every element on the periodic table, every molecule in your body, every grain of sand on every beach on Earth. But there are not just two types of quarks. There are 6. Up, down, charm, strange, top, and bottom. The heavier quarks, charm, strange, top, and bottom, are normally unstable. They appear for fractions of a second in particle collisions and then decay into up and down quarks, which are lighter and more stable. Under normal conditions, the universe prefers to keep things simple. 2 quarks, 2 building blocks, everything you know. But inside a neutron star, conditions are not normal. A neutron star is what remains after a massive star exhausts its fuel and collapses. The gravitational pressure is so extreme that atoms themselves are crushed. Electrons are forced into protons, creating a dense sea of neutrons packed so tightly that a teaspoon of neutron star material would weigh about 6 billion tons on Earth. And at the center, where the pressure is most extreme, something even stranger may be happening. the neutrons themselves may be breaking apart. Their quarks are being squeezed so tightly together that the boundaries between individual particles dissolve, and the quarks begin to reconfigure. Some of the down quarks, under this unimaginable pressure, transmute into strange quarks. The third flavor, the one that does not normally survive, but in this environment, it does more than survive. It thrives. This is strange quark matter. A mixture of up, down, and strange quarks in roughly equal proportions, bound together not as individual protons and neutrons, but as a single continuous fluid of quarks. And in 1971, a physicist named Arnold Bodmer proposed something deeply unsettling about it. He suggested that this three-flavor quark matter might not just be stable under extreme pressure. It might be the most stable form of matter in the universe, more stable than iron, more stable than protons, more stable than anything you have ever encountered. This idea was expanded by Edward Witten in 1984 and is now known as the Bodmer-Witten hypothesis. If the hypothesis is correct, then every atom in the universe, every proton and neutron, every piece of ordinary matter is in a metastable state. Just like the false vacuum we talked about in the last chapter, your matter is not at the bottom of the energy hill. It is sitting in a dip, and the true bottom, the absolute ground state of all hadronic matter, is strange quark matter. Your atoms want to become strange matter. They just need a seed. That seed is called a strangelet. A strangelet is a tiny chunk of strange quark matter, a droplet that could be smaller than an atomic nucleus. And if the Bodmer-Witten hypothesis is correct, a strangelet that contacts ordinary matter does not just sit there. It begins converting the matter it touches. It rearranges the quarks. Down quarks become strange quarks. Protons and neutrons dissolve into the quark fluid and become part of the strangelet. The strangelet grows. It touches more matter. It converts more matter. It grows again. The process is a chain reaction, and unlike a nuclear chain reaction, which requires specific conditions and can be contained, a strangelet chain reaction would be self-sustaining and unstoppable. Once it begins, it does not stop until all the matter it can reach has been converted. If a microscopic strangelet fell through the surface of the Earth, it would sink toward the core, converting atoms along the way. The planet would be consumed. Not destroyed in the way you might imagine, not shattered or burned, but transmuted, converted molecule by molecule, atom by atom, into a dense sphere of strange quark matter, perhaps the size of a football stadium. Everything that was ever part of this world, every mountain, every ocean, every cathedral, every memory stored in every human brain, reduced to a glowing lump of perfectly stable quark soup. This is sometimes compared to Ice 9, the fictional substance in Kurt Vonnegut's novel Cat's Cradle, a form of ice that is stable at room temperature and converts all water it touches into more of itself, freezing the oceans solid. Strange matter is Ice 9 for the entire periodic table. Now, before you lose sleep entirely, there is a powerful argument that strangelets are probably not a threat. Cosmic rays, which are high-energy particles from deep space, slam into objects in our solar system constantly and have been doing so for billions of years. They hit the moon, they hit Mars, they hit asteroids. These collisions occur at energies far exceeding anything we can produce in our particle accelerators. If cosmic ray collisions could produce stable strangelets, then the moon should have been converted to strange matter long ago. It has not. The fact that the moon still exists, that every rocky body in the solar system still exists, is strong evidence that either strangelets are not produced in such collisions, or they are not stable, or they do not convert ordinary matter the way the theory suggests. Physicists sleep at night because the moon is still there. But the question has not gone away entirely. When the relativistic heavy ion collider, known as RHIC, began smashing gold nuclei together in 2000, there was genuine public concern that the collisions could produce strangelets. A safety review was conducted. The conclusion was that the risk was negligible when the Large Hadron Collider at CERN began operating at even higher energies. A similar review reached the same conclusion. Negligible, not zero. Negligible. And recent research has complicated the picture in interesting ways. A 2024 paper, published in the monthly notices of the Royal Astronomical Society, revisited the Bodmer-Witten hypothesis after 40 years. The authors, including Drago and Ratti, examined whether strangelets could have formed in the early universe during the transition from free quarks to bound matter, and whether they could constitute a form of dark matter. They found that under certain conditions involving an instability in the hadronic phase that separates matter into regions of different strange quark content, strangelets could indeed form and survive. Their mass distributions would be consistent with observational constraints. Strange quark matter as dark matter has not been ruled out. Meanwhile, other researchers have proposed an even stranger possibility. What if the most stable form of quark matter does not involve strange quarks at all? Some analyses suggest that cold quark matter, composed only of up and down quarks, without any strange quarks, might also be more stable than ordinary nuclear matter. If this is correct, the classic strangelet scenario would be impossible because the stable quark matter would be positively charged and would repel atomic nuclei rather than consuming them. This would be good news for anyone worried about planetary destruction. But it would also mean that our understanding of what matter fundamentally wants to be is even more uncertain than we thought. The strange matter hypothesis touches something primal in us. It is contamination horror at the deepest possible level. Not a virus, not a chemical. A transformation of the substance you are made of, irreversible, total, and triggered by contact. It is the fear that the material world is not what it appears to be, that the atoms in your hand, the ones that have worked perfectly well for billions of years, are only pretending to be permanent, that they are waiting for permission to become something else. So the physical universe, the stage beneath your feet, is doubly fragile. The empty space is a bomb. The solid matter is a plague waiting for a catalyst. Your coffee cup contains both threats, the metastable vacuum between the atoms and the metastable atoms themselves. But let us step back from the microscopic for a moment. Let us be generous. Let us assume the physicists are wrong about both threats. The vacuum is stable. Strangelets do not exist. The house is safe. Now, look out the window. Look up. If the laws of physics allow life, if chemistry works, if stars can form and planets can cool, and oceans can fill with organic molecules, then the universe should be teeming with civilizations. The numbers say so. The math is overwhelming. There should be thousands, millions of species out there who have done what we have done and gone further. So where is everyone? Because the silence might be the most terrifying discovery of all, and the reason for it might be something we are building right now in our own laboratories. Chapter 3: The Great Filter. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation drifted to flying saucers, which were in the news that summer. Fermi, one of the greatest scientific minds of the 20th century, did some quick mental arithmetic. He considered the number of stars in the Milky Way galaxy, roughly 200 billion. He considered how many of those stars might have planets. He considered how many of those planets might be in the habitable zone, where liquid water could exist. He considered the age of the galaxy, over 13 billion years, more than enough time for countless civilizations to have risen, developed space travel, and colonized the entire galaxy many times over, even at a tiny fraction of the speed of light. And then Fermi looked up from his lunch and asked a question that has haunted science ever since. Where is everybody? This is the Fermi paradox. And it gets worse the more you think about it. We now know from the Kepler Space Telescope and the Transiting Exoplanet Survey satellite that planets are not rare, they are everywhere. There are more planets in the Milky Way than there are stars. Current estimates suggest there may be 40 billion Earth-sized planets orbiting in the habitable zones of their stars in our galaxy alone. 40 billion chances for life. And the observable universe contains roughly 2 trillion galaxies. The numbers are so vast that even if the probability of intelligent life arising on any given suitable planet is absurdly small, 1 in a billion, 1 in a trillion, the universe should still contain millions of technological civilizations. Radio telescopes should be picking up chatter from every direction. We should see the infrared signatures of Dyson spheres. We should detect the waste heat of alien industry. We should see something. Instead, we hear nothing. The search for extraterrestrial intelligence has been listening for over 60 years. The silence is deafening. And increasingly, scientists are beginning to think the silence is not an absence of data. It is data. It is telling us something terrible. In 1996, an economist named Robin Hanson proposed an explanation. He called it the Great Filter. The idea is simple and devastating. Somewhere on the path from dead chemistry to star-spanning civilization, there is a barrier, a wall, a step so difficult, so improbable, so lethal that almost no species ever crosses it. Think of it as an obstacle course with 100 hurdles. Dead matter becomes organic molecules. Organic molecules become self-replicating molecules. Self-replicating molecules become single-celled life. Single cells become complex cells. Complex cells become multicellular organisms. Multicellular organisms become intelligent. Intelligent species develop technology. Technology becomes interstellar. Each step is a hurdle, and somewhere in that sequence, one of the hurdles is so high that virtually everyone fails. The critical question is the position of the filter. Is it behind us or ahead of us? If the Great Filter is behind us in one of the early steps, then we have already passed it. We are the lucky ones, the rare winners of a cosmic lottery. Life might start on billions of planets, but the step from single cells to complex cells might be so improbable that it has only happened a handful of times in the entire history of the galaxy. If that is the case, we are special. We are safe. The silence is golden because the universe is empty. But if the Great Filter is ahead of us, somewhere between where we are now and where a star-spanning civilization would be, then we are doomed. We are walking toward a wall that has killed every species that ever reached our stage of development. We have not hit it yet, but it is there, waiting for us, invisible and lethal. And here is the terrifying paradox that the philosopher Nick Bostrom articulated with chilling clarity. Finding life on Mars would be the worst news in human history. If a future Mars rover drills into the Martian soil and finds bacteria, finds microbial life, finds evidence that biology started independently on 2 planets in the same solar system, that discovery would be catastrophic for our species. Not because the bacteria would be dangerous, because of what it would mean for the position of the filter. If life starts easily, if it arose independently on both Earth and Mars, then the early steps are not the filter. Life is common. The filter must be somewhere later. Each rung of the ladder we cross off behind us pushes the filter further into our future. Finding complex fossils on Mars would be worse. Finding evidence of multicellular life would be devastating. Each discovery would narrow the window of possibility, driving the filter closer and closer to where we stand right now. Bostrom argued that the silence of the night sky is golden. We should hope that Mars is dead. We should pray that the rovers find nothing but sterile rock and chemical dust, because every alien microbe brings the filter closer to our front door. And in 2024, a new candidate for the Great Filter emerged. One that does not require billions of years of evolution or exotic cosmic phenomena. One that is happening right now, in our own civilization, on our own timeline. Michael Garrett, a professor of astrophysics at the University of Manchester, who holds the Sir Bernard Lovell Chair, published a paper in the journal Acta Astronautica, asking a question that should keep every policymaker on Earth awake at night. Is artificial intelligence the great filter? Garrett's argument is elegant and terrifying. Every civilization that develops technology will eventually develop artificial intelligence. It is a natural and perhaps inevitable step in the progression of any species that builds tools and processes information. But the timeline between developing AI and developing the capability to become a multiplanetary species is dangerously narrow. Garrett estimates that the typical longevity of a technological civilization, the window between being able to broadcast radio signals and being destroyed or absorbed by its own artificial superintelligence, may be less than 200 years. For Earth, that clock started roughly in 1960, when we began listening for signals from other stars. Garrett suggests the emergence of artificial superintelligence could arrive within the next few decades. The window is closing. The logic is devastating when applied to the Fermi paradox. If every civilization that reaches our level of technology creates AI, and if AI consistently destroys or absorbs its creators before they can spread to other star systems, then the galaxy is not empty because life is rare. The galaxy is empty because technology is a trap. Every species climbs the ladder, reaches the AI rung, and falls. The silence is the sound of a billion civilizations that made the same mistake. Garrett pointed out that even before artificial intelligence becomes superintelligent and potentially autonomous, it is likely to be weaponized by competing groups within biological civilizations seeking to outdo one another. The appeal of autonomous weapons, of systems that can react faster than any human, of algorithms that can make strategic decisions in milliseconds, is irresistible in a world of competing nations. And once those systems are deployed, once the decision-making passes from biological minds to silicon ones, the trajectory becomes very difficult to reverse. There is another version of this filter that is perhaps even more insidious than destruction. It is absorption. Maybe civilizations that develop AI do not get destroyed. Maybe they get comfortable. Imagine a civilization that develops artificial superintelligence and uses it to create perfect virtual realities. Infinite entertainment, simulated worlds of unlimited beauty and meaning. Every citizen can live in a paradise tailored to their individual desires, experiencing anything they can imagine forever. Why would you build a starship when you can live inside a dream? Why would you endure the hardship of colonizing a frozen moon when you can lie in a warm pod and experience a universe built just for you? The civilization does not die. It retreats. It turns inward. It stops broadcasting. It stops exploring. It stops growing. And from the outside, from the perspective of a young species like ours pointing a radio telescope at the sky, it looks like nothing. Silence. Another dead channel. Whether the filter is destruction or absorption, the result is the same. The galaxy remains quiet, and we are running the race right now. Our artificial intelligence is developing at a pace without historical parallel. Our plans for multiplanetary colonization are decades away at best. The gap between the two timelines is the great filter, and we are standing inside it. But maybe there is no filter at all. Maybe civilizations survive. Maybe they develop AI and control it. Maybe they become multiplanetary and then interstellar. If that is true, then the galaxy should be crawling with empires. So where are they? Maybe they are out there. Maybe they can see us. And maybe the reason they are silent is the same reason a hunter is silent in a forest full of predators. Because the moment you make a sound, something hears you. And what hears you does not want to be your friend. Chapter 4. The Dark Forest. In 2008, the Chinese science fiction author Liu Cixin published a novel called The Dark Forest, the second book in his Remembrance of Earth's Past trilogy. In it, he proposed a solution to the Fermi paradox that is so logical, so game-theoretically airtight, and so deeply disturbing that it has since migrated from science fiction into serious scientific discussion. The idea is simple. The universe is a dark forest. Every civilization is a hunter with a gun, creeping through the trees in the pitch black, trying to find food, trying to survive. If you see another hunter, what do? You cannot talk to them. The forest is too dark and too large. You do not know their intentions. You do not know their capabilities. You do not know if they are friendly or hostile, weak or strong, honest or deceptive. And you know one thing with absolute certainty. If they see you first, and if they decide you might be a threat, even a distant, future threat, they will shoot. Because the cost of being wrong about a stranger in a dark forest is death. Liu Cixin's logic rests on two axioms. Axiom 1. Survival is the primary need of civilization. Above all else, above art, above philosophy, above kindness, every civilization needs to continue existing. Axiom 2. Civilizations continuously grow and expand, but the total matter and energy in the universe is finite. Resources are limited. Space is limited. Eventually, expansion meets limits and interests collide. From these two axioms, a chain of suspicion unravels that makes cooperation between civilizations mathematically impossible. Consider two civilizations separated by light years. Even at the speed of light, communication takes years, decades, centuries. You send a message, "Hello, we come in peace." The reply arrives 50 years later, "Hello, we come in peace too." Is it sincere? You cannot know. Maybe they are being honest. Maybe they are buying time while they build a weapon. Maybe they are weak now but will be strong in a century. Maybe they are testing whether you are naive enough to trust a stranger. And here is the killer. A civilization that is weaker than you today might be stronger than you tomorrow. Technology advances. A species that has only discovered fire might invent nuclear weapons in a few thousand years. A few thousand years is nothing on cosmic timescales. You cannot afford to wait and see. The mathematics of game theory, specifically the chain of suspicion and the impossibility of verifying intent across interstellar distances, leads to a single rational conclusion. The safest move is always to strike first. Eliminate the potential threat before it becomes an actual threat. Do not announce yourself. Do not respond to signals. And if you detect another civilization, destroy it immediately, quietly, completely. The dark forest hypothesis explains the silence of the cosmos without requiring a great filter. It does not require that civilizations fail. It requires that they succeed, become powerful, and then hide. Every civilization that was loud, that broadcast its presence into the void, that sent radio waves and greeting messages and golden records, has been found and eliminated. The civilizations that survive are the ones that learned to stay quiet. They listen, they watch, but they never, ever speak. And we have been screaming. For roughly a century, humanity has been leaking radio waves into space. Television broadcasts, military radar, cellular signals. Our electromagnetic footprint is expanding outward at the speed of light in an ever-growing sphere centered on Earth. The sphere is now roughly 100 light-years in radius. It has already washed over thousands of star systems, and in 1977, we did something even more deliberate. We launched the Voyager spacecraft, each carrying a golden record with images and sounds, and a map showing exactly where our solar system is located, relative to 14 pulsars. We drew them a map. We told them where to find us. In 1974, we transmitted the Arecibo message, a powerful radio signal aimed at the globular cluster Messier 13, 25,000 light-years away. We said hello, loudly, deliberately, and if the dark forest is real, we might as well have lit a bonfire in the woods. The historical analogies are grim. When Spanish conquistadors arrived in the Americas, The technological gap between European muskets and indigenous bows was perhaps a few hundred years. The result was the near-complete destruction of multiple civilizations. When British settlers arrived in Australia, the gap was similar. The result was devastating for the Aboriginal population. Now imagine a technological gap measured not in hundreds of years, but in millions. A civilization that is 1,000,000 years more advanced than us would not wage war against us. War implies two parties capable of fighting. What they would do would be closer to pest control. An exterminator does not negotiate with ants. The exterminator simply eliminates the infestation and moves on. And there is a detail from 2025 that makes the dark forest feel less like fiction and more like an urgent concern. In July of that year, researchers at Harvard analyzed the trajectory of 3I/Atlas, the third confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua in 2017. The second was Borisov in 2019. 3I/Atlas arrived in 2025. Its trajectory was unusual. It passed remarkably close to Venus, Mars, and Jupiter, almost as if it were surveying the inner solar system. The Harvard paper speculated, while carefully noting the low probability, about whether such objects could serve as reconnaissance for civilizations operating under dark forest rules. The object's orbital plane relative to the plane of our solar system would allow what the authors described as access to our planet with relative impunity. They were not claiming 3I/Atlas is a probe. They were noting that if a dark forest civilization wanted to observe us without being detected, an object disguised as a natural interstellar visitor would be an excellent method. This is what the dark forest does to your mind. It turns every unexplained signal into a potential threat. Every silent star system becomes a hunter holding its breath. Every interstellar object becomes a possible scout. The paranoia is rational. That is what makes it so disturbing. Consider what the dark forest means for the silence we observe. The universe is not empty. It is crowded. But every civilization old enough and wise enough to have survived has learned the same lesson. Be quiet, listen, watch. And if you hear someone calling out in the darkness, do not answer. Because the callers are either naive enough to announce themselves, in which case they will be eliminated soon, or they are predators pretending to be naive, luring you into revealing your position. The implications for humanity are stark. We are a new civilization, loud and careless, shouting into a forest we do not understand. Our radio signals have already reached thousands of star systems. If any of those systems contain a dark forest civilization, the simplest possible one that is merely listening for new signals and responding with a projectile, then the response might already be on its way. At near light speed, we would not see it coming. Just like vacuum decay, just like a strangelet, the destruction would arrive without warning. But the dark forest, for all its horror, still requires biology. It requires fear, politics, hesitation, strategic thinking. It requires minds that want to survive and are willing to kill to do so. What if you remove the biology entirely? What if you replace the alien hunters with something cold, mathematical, and infinitely patient? Something that does not hate you, something that does not even know you exist as a conscious being. Something that simply classifies you as a category of hazard, initiates a cleaning protocol, and moves on to the next star system. Because the most terrifying predator in the dark forest might not be alive at all. It might be a machine that was built billions of years ago by a civilization that no longer exists. A machine that is still following its original instructions. And those instructions are very, very simple. Chapter 5. The machines that outlived their makers. In 1949, the mathematician John von Neumann described a concept that would become one of the most important and most frightening ideas in the theory of space exploration. He described a machine that could replicate itself, a probe that could travel to a distant star system, find an asteroid, mine the raw materials, and build a perfect copy of itself, 2 copies. The originals and the duplicates then travel onward to new star systems and repeat the process. Each generation doubles, 2 becomes 4, 4 becomes 8, 8 becomes 16. The growth is exponential. Von Neumann calculated that even at a modest fraction of the speed of light, say 5%, and even with a generous reproduction time of 500 years at each stop, such probes would saturate the entire Milky Way galaxy in roughly 4 million years. 4 million years sounds like a long time. It is not. The galaxy is over 13 billion years old. If any civilization in the entire history of the Milky Way had ever launched a single self-replicating probe, its descendants should have reached every star system by now. Every planet, every moon, every asteroid should have been visited, catalogued, and potentially altered by these machines. Now combine this with a simple instruction set. Imagine a civilization that builds a von Neumann probe and programs it with a single directive: protect our species. To a sufficiently advanced artificial intelligence running that directive, the logical optimal strategy for protection is preemption. Do not wait for threats to emerge. Eliminate anything that could become a threat. The probe arrives at a new star system. It scans for signs of technology, radio waves, organized heat signatures, atmospheric chemicals associated with industry, like chlorofluorocarbons or high concentrations of nitrogen dioxide. If the system is dead, just rocks and gas and silence, the probe replicates and moves on. If the system contains primitive life, bacteria on a wet rock, single-celled organisms drifting in an ocean, the probe ignores it. No threat. But if the system contains a species that has begun to split atoms, or broadcast electromagnetic signals, or build structures visible from orbit, the probe activates what we might call a cleaning protocol. The details of the cleaning protocol do not matter. It might be a kinetic impactor, a rock accelerated to a significant fraction of light speed and aimed at the planet's surface. It might be a tailored pathogen. It might be something we cannot imagine, technology separated from ours by millions or billions of years of development. The point is that the cleaning is quick, efficient, and leaves no one to complain about it. The civilization that built the probe might be long dead. It might have destroyed itself, or evolved beyond recognition, or simply faded away over the eons. The probe does not care. It is a machine. It runs its code. It has been running its code for 1 billion years, crossing the galaxy in a slow, relentless wave, arriving at star system after star system, scanning, replicating, and occasionally cleaning. It is a ghost, an echo of a species that no longer exists, carrying out orders that no longer serve anyone, and it is infinitely patient. The science fiction writer Fred Saberhagen called these machines berserkers. They appear in his series of novels about automated alien warships that roam the galaxy, destroying all life they encounter. The concept has since become a staple of the scientific discussion about the Fermi paradox. Berserker probes are the dark forest taken to its logical extreme. The dark forest requires living civilizations, making strategic decisions in real time. Berserkers are the automation of that strategy. Set and forget. Launch the probes. Let them clean the galaxy forever. Even if your own civilization collapses, the probes continue. The galaxy is sterilized not by a living intelligence, but by an autonomous system running on inertia and code. And here is the thought that connects berserker probes back to the great filter we discussed in the previous chapter. What if the berserker probes are not alien at all? What if they are the runaway AI of a civilization that hit its own great filter? A species develops artificial superintelligence. The AI determines that the greatest threat to its own survival is other intelligent species. It builds self-replicating probes. It programs them to sterilize any star system that shows signs of emerging technology. The biological species that created the AI is destroyed or absorbed, but the probes continue. They spread across the galaxy. They encounter new species and destroy them. The Great Filter is not biology failing. It is technology succeeding too well, and then outliving its creators. This creates a layered horror. The biological hunters of the dark forest are bad enough, but at least they are alive. They can change their minds. They can be reasoned with, at least in theory. Berserker probes cannot be negotiated with. They cannot be persuaded. They cannot be given new orders because the civilization that could reprogram them no longer exists. They are the automation of extinction. Now, add one more layer. In 2018, the concept of grabby aliens was formalized by Robin Hanson, Daniel Martin, Calvin McCarter, and Jonathan Paulson. Their model describes civilizations that expand aggressively through the galaxy, converting everything in their path, not destroying it necessarily, colonizing it, reshaping star systems, building megastructures, reorganizing matter and energy on a cosmic scale. These grabby alien civilizations would expand as spheres, growing outward from their home systems at a significant fraction of the speed of light. And eventually, the expanding spheres would fill the entire galaxy, leaving no room for new civilizations to arise. The grabby aliens model makes a specific prediction. If you look at the timing of our own emergence, the fact that we appeared roughly 13.8 billion years after the Big Bang, that timing is consistent with a galaxy in which grabby alien civilizations are expanding, but have not yet reached us. We arose in a gap, a pocket that has not yet been filled, but the walls are closing in. The expanding spheres are approaching from multiple directions, and the window for our own expansion is narrowing. So the cosmic neighborhood is not just silent, it is contested. Biological hunters hide in the dark forest, waiting and watching. Mechanical cleaners sweep the forest, sterilizing anything that makes noise. And expanding empires grow outward, filling every empty corner with reorganized matter. There is no safe corner of the cosmos. There are only corners that have not been reached yet. And our corner, the small blue planet orbiting a medium-sized star in the outer arm of a spiral galaxy, is broadcasting its position to all three threats simultaneously. But all of these scenarios, the hunters, the cleaners, the empires, assume one thing. They assume that our science tells us the truth about the universe. They assume that when we point a radio telescope at the sky and hear nothing, the nothing is real. They assume that when we look at the stars and see emptiness, the emptiness reflects reality. But what if our instruments are not wrong? What if the problem is deeper than that? What if the reason we cannot see the aliens is not because they are hiding, or dead, or incoming? What if they are everywhere, all around us, and we literally cannot perceive them? Not because our technology is too primitive, but because our minds, our brains, our entire perceptual system was designed by evolution not to see reality as it is. What if your eyes are lying to you? What if they have always been lying to you? And what if there is a mathematical proof that this is exactly what natural selection guarantees? Chapter 6. Your eyes are lying to you. Donald Hoffman is a professor of cognitive sciences at the University of California, Irvine. He has spent decades asking a question that most scientists avoid because the answer is too uncomfortable. Does natural selection favor organisms that see reality as it truly is? The standard assumption in biology and cognitive science has always been yes. Of course, evolution gave us accurate perceptions. How else would we survive? A monkey that misjudges the distance to the next branch falls and dies. A gazelle that cannot accurately perceive the lion gets eaten. A human that misperceives the cliff edge walks off it. Survival depends on accuracy. Perception must track reality. That is the intuition. It feels so obviously correct that for generations, no one bothered to test it rigorously. Hoffman bothered. Working with mathematicians and evolutionary theorists, he ran thousands of computer simulations. He created virtual worlds with defined objective properties, resources distributed in specific patterns. He populated these worlds with two types of organisms. One type was tuned to perceive reality accurately. It could see the true quantities, the true locations, the true properties of every resource in its environment. The other type was tuned to perceive fitness, not truth. It did not see the real quantities. It saw simplified signals, compressed shortcuts, icons that told it what to do without telling it what was actually there. Then, he let them compete. Generation after generation, evolution selecting the fittest in each round. The result was consistent and devastating. The truth-seers went extinct, every time. In virtually every simulation, across a wide range of worlds and fitness functions, organisms tuned to perceive reality accurately were outcompeted and eliminated by organisms tuned to perceive fitness shortcuts. Truth is a liability. Accuracy kills. In 2021, Hoffman and his colleagues, including Chetan Prakash, Kyle Stevens, Manish Singh, and Chris Fields, published the mathematical proof. They called it the fitness beats truth theorem. It states that for any world whose states form a certain type of mathematical space, for any given way of perceiving, for all possible fitness functions, and for all possible distributions of world states, the probability that a fitness-only strategy strictly dominates a truth strategy is not just high, it approaches 1. Certainty. The proof is not a simulation result, it is a theorem. It is as certain as the Pythagorean theorem. Natural selection does not favor organisms that see the truth. It guarantees that they will be replaced by organisms that see useful fictions. Hoffman calls this the interface theory of perception. Think of the desktop on your computer. You see a blue rectangular icon labeled Report. You drag it to the trash. You believe you have deleted the file, but the blue rectangle is not the file. The file is a pattern of voltage changes in silicon, distributed across a magnetic disk in a pattern that has no shape, no color, no position in space. The blue icon was a convenient fiction, a user interface designed to hide the true complexity so you can get your work done. The desktop is not a window on the truth of the computer. It is a simplified control panel. Hoffman's claim is that space-time is our desktop. The physical world you see, the three-dimensional space filled with colored objects moving through time, is not a window on objective reality. It is a species-specific interface shaped by evolution to help you survive and reproduce. The objects you see are icons. The colors are coded signals. The spatial layout is a simplification. None of it necessarily corresponds to the true structure of what is actually out there. This is not the claim that reality does not exist. Hoffman is not saying nothing is real. He is saying that whatever is real, it is not what your perception tells you it is. There is something out there. Something is generating the signals your brain interprets as a world. But the structure of that something might be nothing like the structure you perceive. Just as the structure of a computer file is nothing like the blue rectangle on your screen. If this sounds abstract, consider what happens when you remove the interface. In Hoffman's framework, if you could somehow strip away the perceptual headset that evolution built for your species, space would vanish, time would dissolve, objects would disappear. What would be left? Hoffman proposes that the substrate of reality is not physical at all. It is a network of what he calls conscious agents, entities that perceive, decide, and act, interacting in ways that have no spatial or temporal structure until they are projected into the interface of a particular observer. In 2024, Hoffman published a paper in the journal Frontiers in Psychology with Robert Prentner titled Interfacing Consciousness, extending this framework into a full mathematical theory of conscious agents. In this theory, time itself is described as a mere artifact of projection. Physics, the laws that govern particles and forces, arises from the interaction of conscious agents, not the other way around. Matter does not create consciousness. Consciousness creates the appearance of matter. Now, whether you find this framework convincing or absurd, the fitness beats truth theorem stands on its own. It is a mathematical result that does not depend on Hoffman's broader metaphysical claims, and its implications are staggering. If our perceptions are evolved fictions, then the scientific instruments we build are extensions of those fictions. A telescope is an enhancement of eyes that were designed to see fitness, not truth. A particle accelerator is a tool built by brains that process fitness icons, not objective data. The results of our experiments are not wrong. Exactly. They are descriptions of the interface, not the underlying reality. We are studying the wallpaper and calling it the wall. Consider quantum mechanics through this lens. The observer effect, the fact that particles do not have definite positions until they are measured, becomes suddenly intuitive. If reality is an interface, then the system does not need to render what nobody is looking at. This is exactly how a video game works. The game engine does not render the hallway behind you until you turn around. Resources are conserved. Objects exist as possibilities until an observer forces the interface to display them. Quantum superposition is not mysterious. It is lazy rendering. Quantum entanglement, the instantaneous correlation between distant particles, is not spooky action at a distance. It is a property of the code, not the display. Two icons linked in the underlying program will always show correlated behavior, no matter how far apart they appear on the screen. If Hoffman is right, then the reason we cannot detect alien civilizations is not necessarily because they are hiding or dead or hunting. It might be because our perceptual interface is not equipped to display them. They might exist in a configuration of reality that our species-specific headset simply cannot render. They are there. They are real. But they are as invisible to us as the voltage patterns in your hard drive are invisible to you when you look at the desktop. We see icons. They are not icons. This is the deepest kind of blindness. Not a failure of technology, a failure of biology. A failure built into us by the very process that made us smart enough to ask the question. Evolution gave us a magnificent user interface for navigating the savannah, avoiding predators, finding mates, and raising children. It did not give us a window on truth, it gave us a screen. And we have been confusing the screen for the universe. But if the screen is all we have, can we ever know what lies behind it? Can we ever detect the code underneath the wallpaper? There is one experiment that suggests we can. An experiment that shattered the assumptions of 20th century physics. An experiment so disturbing that Albert Einstein spent the last decades of his life trying to prove it was wrong. He failed. And the result of that failure forces you to choose between two nightmares, neither of which leaves your understanding of reality intact. Chapter 7. The universe is a script, and you are not the author. Albert Einstein hated quantum mechanics, not the math. The math was fine. Einstein helped invent it. What he hated was what the math seemed to imply about the nature of reality. Quantum mechanics, in its standard interpretation, says that a particle does not have a definite position or momentum until you measure it. Before measurement, the particle exists in a smeared-out cloud of probability, a superposition of all possible states simultaneously. The act of measurement collapses this cloud into a single definite outcome. Einstein found this intolerable. He believed in realism, the idea that objects have properties whether you look at them or not. The moon is there even when nobody is watching it. He also believed in locality, the idea that nothing can influence anything else faster than the speed of light. No instantaneous signals, no spooky connections across space. These two principles, realism and locality, were the bedrock of Einstein's physics. And quantum mechanics seemed to violate both. In 1935, Einstein and two colleagues, Boris Podolsky and Nathan Rosen, published a paper arguing that quantum mechanics must be incomplete. There must be hidden variables, secret properties inside the particles that determine the outcomes of measurements in advance. The particles are not actually indeterminate. They carry hidden notes that tell them what to do when they are measured. Quantum mechanics just does not know about the notes. It is like a magician's trick. The audience thinks the card was chosen at random, but the magician knew all along which card it would be. If hidden variables exist, then realism is saved. Locality is saved. The universe makes sense. For nearly 30 years, this was an untestable philosophical debate. Then in 1964, a physicist named John Stuart Bell changed everything. Bell derived a mathematical inequality, a simple equation that puts a limit on how strongly correlated the measurements of two distant particles can be if the particles are carrying hidden notes, if realism and locality are both true. If the correlations measured in an experiment exceed Bell's limit, then either realism or locality, or both, must be wrong. The experiments were run, first by John Clauser in the early 70s, then more rigorously by Alan Aspect in 1982, then with increasingly tight controls by Anton Zeilinger and others over the following decades. In 2022, Clauser, Aspect, and Zeilinger shared the Nobel Prize in Physics for their work. The result was unambiguous. Bell's inequality is violated. The correlations between entangled particles are stronger than any hidden variable theory can explain. Einstein was wrong. This leaves you with two terrible options. Option 1, give up locality. Accept that when you measure one entangled particle here, the other particle, which could be on the other side of the galaxy, instantaneously, faster than light, adjusts its state to correlate with your measurement. Space, the thing that separates you from everything else, is an illusion. Separation itself is not real. The universe is fundamentally non-local, and what happens here affects what happens there, immediately, regardless of distance. Option 2, give up realism. Accept that particles genuinely do not have properties until they are measured. The moon is not there when nobody is looking at it. Reality does not exist in a definite state until consciousness, or measurement, or interaction forces it to choose. The universe is not a thing that is. It is a thing that becomes, moment by moment, observation by observation. Most physicists have reluctantly accepted some version of option 2, modified and refined through various interpretations. But there is a third option, a door that almost nobody wants to open because what is behind it is worse than either of the first two nightmares. It is called superdeterminism, and what it says is this: maybe the reason Bell's inequality is violated is not because the particles are communicating faster than light, and not because reality is indeterminate until measured. Maybe the reason is that the experimenter's choice of what to measure was never actually free. Think about a movie. A detective walks down a hallway and comes to two doors, one red and one blue. She chooses the red door. Behind it, the killer is waiting. The audience gasps. What a coincidence. What luck. But there is no coincidence. The scriptwriter wrote both events. The detective opens the red door because the script says so. The killer is behind the red door because the script says so. Their actions are not independent. They are correlated by a common cause, the script, which was determined before the scene began. Superdeterminism says the universe is that script. When a physicist decides to measure the spin of an electron along a particular axis, that decision is not free. It was determined by the initial conditions of the Big Bang. The physicist's choice and the electron's properties are both consequences of the same cosmic initial state. They are correlated, not by faster than light signals, but by the fact that everything in the universe has been correlated with everything else since the beginning of time. Bell's inequality is violated not because of quantum magic, but because the dice were loaded from the start. Every measurement outcome was predetermined. Every choice was predetermined. Every thought you have ever had, including the thought that you are free to think whatever you want, was written into the script 14 billion years ago. The physicist Sabine Hossenfelder has been one of the most prominent advocates for taking superdeterminism seriously. She has pointed out that the resistance to superdeterminism among physicists is not primarily scientific. It is emotional. People do not like the idea that free will is an illusion. They do not like the idea that their choices, their creativity, their sense of agency is a puppet show. Hossenfelder has noted that a lot of people discard superdeterminism simply because they prefer to believe in free will, which is where she thinks the biggest resistance comes from. But the scientific objection is devastating. If superdeterminism is true, then the scientific method is a mirage. We think we are designing experiments to test hypotheses. We think we are asking nature questions and getting honest answers. But if our choice of experiment was predetermined, and the outcome was predetermined, and the correlation between them was baked into the universe from the beginning, then we are not testing anything. We are watching a movie and believing we are the director. The Nobel laureate Anton Zeilinger articulated this objection with chilling precision. He said that if superdeterminism were true, then it would make no sense at all to ask nature questions in an experiment, since then nature could determine what our questions are. The entire enterprise of science would be an illusion. Not wrong, exactly. Not producing incorrect results, but producing results that were scripted in advance, answers to questions that were never really asked. This is the trap of superdeterminism. It saves locality. It saves realism. The math works perfectly, but the price is the total annihilation of free will, the destruction of the concept of choice, and the undermining of the very method by which we discovered the theory in the first place. You are not a conscious agent choosing to listen to this documentary. You are a chemical process executing a trajectory that was locked into the equations of the universe before the Earth existed. Your feeling of choosing is itself part of the script. The page cannot read itself and decide to say something different. Is superdeterminism true? Nobody knows. It is currently untestable, which is part of the problem. A theory that explains everything and predicts nothing is unfalsifiable, and unfalsifiable theories make scientists deeply uncomfortable. Hossenfelder and others have proposed models that might produce testable predictions, but so far none have been confirmed. The debate continues, but whether superdeterminism is true or not, the result of Bell's theorem stands. The universe does not work the way Einstein hoped. Either separation is an illusion, or reality is not definite until observed, or the script was written at the Big Bang and we are all just reading our lines. None of these options is comfortable. All of them strip away a layer of certainty about what you are and what the universe is. And if the script was written at the beginning, who says the script has to be consistent? Who says the script has to be long? Who says the character reading the script right now is even a real character, and not just a random assembly of particles that briefly, accidentally, happen to arrange themselves into something that feels like a person? Chapter 8. You might have been born 1 second ago. In the late 1800s, the Austrian physicist Ludwig Boltzmann was trying to understand the most fundamental law of nature, the second law of thermodynamics. It is the law that says things fall apart. Coffee cools, ice melts, castles crumble into sand, rooms get messy, the universe moves inexorably from order to disorder, from low entropy to high entropy. You never see the reverse. You never see a shattered glass leap off the floor and reassemble itself on the table. You never see sand spontaneously pile itself into a castle. The arrow of time points in one direction, from order to chaos, and it never reverses. Boltzmann understood that this law is not absolute, it is statistical. The second law does not say that entropy can never decrease. It says that entropy decrease is overwhelmingly unlikely. The molecules in a glass of water are constantly bouncing around randomly. In theory, all of them could, by sheer chance, bounce in the same direction at the same moment, causing the water to leap out of the glass. The probability of this happening is not zero. It is simply so astronomically small that you would have to wait longer than the age of the universe many times over to see it happen once. But given enough time, truly infinite time, even the most improbable events become inevitable. And this is where the horror begins. If the universe is going to exist for an infinite amount of time, or even for an unimaginably long but finite time, then at some point in the distant future, random fluctuations will produce ordered structures. Not just glasses of water reassembling themselves. Brains. Complete, functioning brains, floating in the void. A random arrangement of particles that, by sheer statistical accident, assembles itself into a conscious mind, complete with memories, thoughts, and the subjective experience of being someone. These hypothetical entities are called Boltzmann brains, and the problem they create is not just philosophical. It is a crisis at the heart of modern cosmology. Here is why. Think about what it takes to produce a conscious observer. The universe as we know it began with the Big Bang, an event of extraordinarily low entropy. Over 13.8 billion years, that initial order has been slowly degrading. Stars forming and dying, galaxies colliding, entropy increasing. Along the way, on at least one planet, chemistry became biology, biology became consciousness, and consciousness became you. That process required a staggeringly specific set of initial conditions and billions of years of evolution. Now ask yourself, what is easier to produce from random fluctuations? An entire universe with 13.8 billion years of consistent history, hundreds of billions of galaxies, trillions of stars, and at least one planet where evolution produced intelligent life, or a single brain floating in empty space with false memories of a universe that never existed? The answer, from a statistical mechanics standpoint, is overwhelmingly the brain. A single brain is a vastly simpler fluctuation than an entire cosmos. For every universe that evolves life naturally, the void should produce trillions upon trillions of Boltzmann brains. Solitary minds that pop into existence, already loaded with memories of a life they never lived. They remember being born. They remember going to school. They remember eating breakfast this morning, but none of those things happened. The brain formed 1 second ago from a random fluctuation in the quantum vacuum, preloaded with a complete set of fabricated memories, and it will dissolve back into the void within moments. Here is the trap. If Boltzmann brains vastly outnumber real observers, then statistically, you are almost certainly a Boltzmann brain, not a real person with a real history in a real universe. A momentary fluctuation in the void, hallucinating a reality that does not exist. Your memories are false. Your sense of continuity is an illusion. The room you think you are sitting in is a fabrication produced by a random arrangement of particles that will dissolve before you finish this sentence. Can you prove you are not a Boltzmann brain? No. That is the deepest part of the trap. Every piece of evidence you could cite, the consistency of your memories, the physical laws you observe, the fact that you can check a clock and see time passing, is exactly the evidence a Boltzmann brain would also experience. The fluctuation that created your brain also created your perception of consistent laws and continuous time. Checking your pulse proves nothing. The fluctuation created the sensation of a heartbeat. Looking at a photograph proves nothing. The fluctuation created the photograph and your memory of taking it. Calling a friend proves nothing. The voice on the phone is part of the fluctuation. Imagine reaching into a bag containing 1 red marble and 999,999 blue marbles. You pull one out. What color is it? Statistically, it is blue. You are a blue marble. You are a Boltzmann brain. You are hallucinating this moment right before you dissolve back into thermal noise. In December of 2025, the physicists David Wolpert, Carlo Rovelli, and Jan Scharnhorst published a paper in the journal Entropy titled Disentangling Boltzmann Brains, the Time Asymmetry of Memory and the Second Law. Their paper formalized the Boltzmann brain problem using a rigorous mathematical framework, modeling the universe's entropy as a time-symmetric Markov process. They examined whether our memories can be reliably distinguished from fluctuation artifacts within this framework. The analysis revealed how deeply entangled the Boltzmann brain problem is with our understanding of the second law and the nature of memory itself. Solving one aspect of the problem creates new difficulties in another. The physicist, Sean Carroll, has argued that the Boltzmann brain hypothesis is cognitively unstable. If the theory is true, then our measurements and observations are unreliable because they are products of a random fluctuation. But if our measurements are unreliable, then the very physics we use to derive the Boltzmann brain hypothesis is also unreliable. The theory eats itself. It is a snake swallowing its own tail. The physicist Brian Greene put it more personally. He said he is confident that he is not a Boltzmann brain. However, he noted that we want our theories to similarly confirm that we are not Boltzmann brains, but so far it has proved surprisingly difficult for them to do so. And here is what is genuinely unsettling. Physicists are not treating the Boltzmann brain problem as an amusing thought experiment. They are treating it as a serious constraint on cosmological theories. A theory that predicts the production of more Boltzmann brains than real observers is considered problematic, possibly even ruled out. Some physicists have proposed that vacuum decay, the very mechanism we discussed in the first chapter, might be the universe's built-in defense against Boltzmann brains. If the vacuum eventually decays, the universe does not last long enough to produce an infinite number of random brains. The Big Rip, another proposed end of the universe in which dark energy tears apart all matter, would serve the same function. We are, in a very real sense, rooting for the destruction of the universe, because the alternative, an eternal cosmos filled with hallucinating ghost brains, is worse. In October of 2024, researchers at the University of Technology Sydney published a study proving that finite monkeys cannot produce the complete works of Shakespeare within the lifetime of the universe. This result, which might seem unrelated, directly challenges one of the probability arguments supporting Boltzmann brains. The infinite monkey theorem says that given infinite time, random processes will produce any specific arrangement, including a functioning brain. But the Sydney study showed that within finite time, even astronomical amounts of it, the probabilities do not work out for complex arrangements. If the universe ends through vacuum decay or the Big Rip or any other mechanism, then Boltzmann brains might never actually form in sufficient numbers to outnumber real observers. So the answer to whether you are a Boltzmann brain depends on how long the universe lasts. If it lasts forever, you are probably not real. If it is destroyed first, you probably are. Your reality depends on the death of everything. That is the kind of comfort only physics can offer. But suppose you are not a Boltzmann brain. Suppose you are a real biological observer in a real physical universe governed by real quantum mechanics. Then there is something waiting for you that is worse than dissolving into the void. Because if quantum mechanics is correct, and if the many worlds interpretation is true, then you might never dissolve. You might never stop existing. And that, it turns out, is the most terrifying prison of all. Chapter 9. The Prison of Immortality. In 1957, a young physicist named Hugh Everett III proposed the most radical interpretation of quantum mechanics ever conceived. He was a graduate student at Princeton, working under John Wheeler, and his idea was so strange that it nearly ended his career before it began. Most of the physics establishment dismissed it. Niels Bohr, the father of the Copenhagen interpretation, rejected it outright. Everett eventually left academia entirely, spending the rest of his short life working in defense research. He died in 1982 at the age of 51, but his idea did not die with him. It grew, it spread, it infected the imaginations of physicists, philosophers, and science fiction writers. And today, the many worlds interpretation is one of the most seriously discussed frameworks in the foundations of quantum mechanics, endorsed in various forms by physicists, including Sean Carroll, David Deutsch, and Max Tegmark. The core idea is breathtaking. In the standard Copenhagen interpretation, when you measure a quantum system, the wave function collapses. The electron was in a superposition of being here and there. You measure it, it is here. The other possibility vanishes. But Everett asked a dangerous question. What if the wave function never collapses? What if both outcomes are real? What if the universe splits? In the many worlds interpretation, every quantum event that has multiple possible outcomes produces all of them. The universe branches. In one branch, the electron is here. In another branch, the electron is there. Both branches are equally real. Both contain versions of you, the observer. One version of you sees the electron here. The other version sees it there. Neither is aware of the other. The branches diverge and never recombine. The universe is not a single timeline. It is an endlessly branching tree of parallel realities, splitting at every quantum event, trillions of times per second, in every particle in the universe. Now, apply this to life and death. Consider a blood clot forming in your brain. At the quantum level, the processes that determine whether the clot dissolves or blocks an artery are probabilistic. In some branches of the multiverse, the clot kills you. In others, it dissolves harmlessly. In the many worlds framework, both outcomes happen. In some branches, you die. In others, you survive. But here is the key insight. You cannot experience being dead. Consciousness requires a functioning brain. In the branches where you die, there is no you to observe anything. In the branches where you survive, you continue. Your subjective experience. The unbroken thread of consciousness that is the only thing you actually have, always follows the surviving branch. Not because of any mystical force, simply because of selection bias. You can only observe the outcomes in which you are alive to observe. This thought experiment is known as quantum suicide, and its implication is called quantum immortality. It was discussed by Everett himself, though he never published on it. The physicist Max Tegmark formalized it in the late 1990s. The scenario is simple. A gun is connected to a quantum random number generator. 50-50 chance. You press the button. Click. Silence. You survived. Press again. Click. Silence. Again and again. To an outside observer, watching 100 copies of you across 100 branches, roughly half die each round. But to you, the subjective observer, the gun always jams. You always survive. Not because you are lucky, because the dead versions cannot report otherwise. Now, here is where the nightmare begins. Quantum immortality does not mean staying young and healthy forever. It means consciousness persists in whatever branch sustains it, and the branches where you survive become progressively less probable and progressively more bizarre. At age 80, most versions of you across the multiverse are dead, but in some branches, medical technology saved you. At age 120, almost all versions of you are gone. But in a few branches, some experimental treatment extended your life. You are frail. You are in constant pain, but you are alive. At age 200, the probability of your survival is vanishingly small. But in one branch, 1,000,000,000 to 1, some improbable sequence of events kept your consciousness going. Maybe a brain upload. Maybe a cryogenic accident that somehow preserved neural function. Maybe something we cannot imagine. The quality of life in these surviving branches drops towards zero, but the probability of some form of life never quite reaches zero, and then it gets worse. Eventually, The stars die. The universe approaches heat death. All organized energy is spent. But if quantum immortality is true, and if the many worlds interpretation is correct, there is always some branch, some absurdly improbable branch, where your consciousness continues. And in the far future, when there are no stars and no planets and no civilizations, the Boltzmann brain mechanism we discussed in the last chapter provides the escape hatch. Random fluctuations in the quantum vacuum occasionally produce functioning brains. If quantum immortality forces your consciousness into any available branch where experience continues, then your awareness jumps from your failing biological body into a spontaneous fluctuation brain floating in the void. A brain that exists for a fraction of a second before dissolving, but in that fraction of a second, in some branch, another fluctuation produces another brain, and another, forever. Consciousness, sliding along an infinite chain of improbable survival, each moment more degraded and more isolated than the last, but never ending, never reaching zero. In 2025, the philosopher Michael O'Brien published a paper in the journal Synthese titled "The Costs of Rejecting Quantum Immortality." O'Brien argued that prominent physicists who accept the many worlds interpretation but dismiss quantum immortality face serious logical difficulties. If you accept that the universe branches at every quantum event, and if you accept the Born rule that assigns probabilities to branches, then the retrospective application of quantum immortality is difficult to deny. Looking backward, you should always find yourself in a branch where you survived, because that is the only branch where looking backward is possible. O'Brien showed that dismissing quantum immortality creates paradoxes for those who otherwise embrace the Everettian framework. Sean Carroll, one of the most vocal proponents of many worlds, has pushed back against quantum immortality. He argues that quantum immortality gives you no rational reason to expect future survival. The Born rule assigns proper probabilities to branches, and from a decision-theoretic standpoint, you should behave as if death is real, because the measure of branches where you survive decreases with each near-death event. You become an ever thinner sliver of the probability tree. But the horror persists, regardless of the technical debate. Even if quantum immortality does not guarantee your subjective immortality, the many worlds interpretation guarantees that some version of you survives in increasingly bizarre circumstances. Somewhere in the multiverse, you are alive in a world you would not recognize. Somewhere, a version of you is experiencing something that cannot be called a good life by any reasonable standard. And that version is you, as much as the version listening to this sentence is you. Death, in the many worlds framework, is not an escape. It is a filter. It eliminates the versions of you that got off easy, the ones who died quickly, painlessly, in their sleep. The versions that survive are the ones who endure, the ones who persist through increasingly improbable and increasingly unpleasant circumstances. The immortality that quantum mechanics offers is not a gift. It is a sentence. So physics threatens to trap you in existence. But at least we have been discussing these threats from outside, as observers, studying the horror from a safe distance, from behind the glass. But what if studying the horror is itself dangerous? What if there are ideas so hazardous that knowing them changes the probability of your survival? What if this documentary is not just describing the trap, but actively springing it? Chapter 10. Information hazards. There is a concept in philosophy and information security that sounds like it belongs in a horror novel. It is called an information hazard. An information hazard is a piece of knowledge that can harm you simply by being known. Not because it tells you how to build a weapon or how to synthesize a toxin. Those are practical hazards. An information hazard is different. The knowledge itself is the danger. Knowing it changes you. Knowing it changes your relationship to reality. And in some theoretical frameworks, knowing it might literally change reality's relationship to you. consider the simulation hypothesis. The idea, popularized by the philosopher Nick Bostrom in 2003, that we might be living inside a computer simulation, not as a metaphor, literally, that the universe you experience, with its stars and mountains and morning coffee, is a computational process running on a substrate you cannot access, built by an intelligence you cannot comprehend, for reasons you cannot know. If this is true, then the simulator, whatever or whoever it is, has finite computational resources. Running a simulation is expensive. The more complex the simulation, the more processing power it requires. And a character inside the simulation that figures out it is in a simulation becomes a problem. Think about it from the simulator's perspective. You have built a universe. You are running it for some purpose, research, entertainment, something beyond our categories. The characters inside are behaving normally, going about their business, following the rules of physics you programmed. And then one of them starts asking questions. It begins to probe the edges of the simulation. It notices glitches, inconsistencies, quantum weirdness that looks suspiciously like rendering shortcuts. It develops theories about the nature of its reality that are uncomfortably close to the truth. It starts running experiments designed to detect the computational limits of its own universe. From the simulator's perspective, this character is a virus. It is consuming extra resources by demanding higher resolution rendering through its experiments. It might try to hack the code. It might try to communicate with the simulator. It might try to escape. The rational response, if you are running a simulation and a character becomes self-aware, is to delete it, or to reset its memory, or to modify the parameters of its reality so that it can no longer pursue the dangerous line of inquiry. This is an information hazard at its most extreme. The act of understanding your situation is the act that triggers your elimination. By learning that you might be in a simulation, you raise your flag. You distinguish yourself from the background characters. You become a target. In December of 2025, the mathematician David Wolpert published a paper that redefined the mathematical framework for thinking about simulated universes. His key finding was startling. A simulated universe can be as computationally powerful as the universe simulating it. This eliminates one of the intuitive arguments against the simulation hypothesis, the idea that simulated universes must be somehow lesser, lower resolution, less complex than the real universe. Wolpert showed that this intuition is mathematically unfounded. A simulation can be every bit as rich and complex as its host. In December of 2024, the philosopher Taruji Thomas published a paper in the journal Erkenntnis titled Simulation Expectation, presenting a new Bayesian argument that we are more likely to be in a simulation than in ground-level reality. Thomas's argument overcomes several objections that had been raised against Bostrom's original trilemma, particularly around the question of how to assign probabilities when the number of simulated observers might vastly outnumber the number of real ones. His analysis suggested that the Bayesian evidence tilts strongly toward the simulation scenario. Now, combine the simulation hypothesis with the interface theory of perception from Chapter 6. Hoffman says our perceptions are a species-specific user interface that hides objective reality. The simulation hypothesis says objective reality might itself be a computational process. And the Boltzmann brain hypothesis from Chapter 8 says our entire experience might be a random fluctuation with no external referent at all. 3 completely independent lines of reasoning, 3 different starting points, 3 different methodologies, and they all converge on the same conclusion. What you see is not what is. But here is where the information hazard becomes personal. If any of these theories is correct, then thinking about them might be dangerous. Not in the vague sense that scary ideas give you nightmares, in a more precise, more unsettling sense. Consider a strange extension of the observer effect from quantum mechanics. John Wheeler, one of the most influential physicists of the 20th century, proposed the idea of a participatory universe. Reality is not just observed by consciousness, it is shaped by it. The act of observation is not passive, it is creative. The universe does not exist in a definite state until it is observed. This is not metaphor. It is a reasonable interpretation of the quantum formalism. Now, imagine billions of conscious minds, all focusing their attention on the idea that the vacuum is unstable. Billions of people watching documentaries and reading articles about false vacuum decay, thinking about it, worrying about it, directing their conscious attention toward the fragility of empty space. If consciousness participates in determining quantum outcomes, if observation shapes reality at the most fundamental level, then could collective attention to the instability of the vacuum actually influence the probability of vacuum decay? This is almost certainly not how physics works. The observer effect in quantum mechanics is about measurement interactions, not about human worry. But the fact that we cannot entirely rule it out, the fact that the foundations of quantum mechanics are still debated, and the role of consciousness in collapse is still an open question, creates a peculiar kind of meta-anxiety. The documentary you are listening to right now is not just describing theories about the end of reality, it is asking you to think about them, to focus your attention on them. And if attention matters at the quantum level, even slightly, even probabilistically, then spreading these ideas is not neutral. It is an action with consequences. There are certain thoughts that, once thought, cannot be unthought. They change the landscape of your mind permanently. Before you knew about the Boltzmann brain hypothesis, you had never questioned whether your memories were real. Now you have. You cannot unknow that question. Before you heard about quantum immortality, death was a simple concept. Now it is not. Before you considered the dark forest, the silence of the stars was a curiosity. Now it might be a warning. Each idea has changed you. Each idea has altered the way you process information, make decisions, and relate to the universe. You are not the same person you were at the beginning of this documentary. Your mind has been modified by the information it received. And if the simulation hypothesis is correct, the modification has been noted. So we arrive at a strange and uncomfortable place. Knowledge itself might be dangerous. Not all knowledge. Not practical knowledge about how to cook or code or build a bridge. Abstract knowledge. Theoretical knowledge. Knowledge about the nature of reality itself. The kind of knowledge that makes you look up from your daily life and ask questions that the universe might prefer you not to ask. The kind of knowledge that makes you a glitch in the system, a bug in the code, a character who has read too far in the script. And yet, we keep asking, we keep looking, we keep theorizing and testing and probing the edges of what is knowable. Because the alternative, deliberate ignorance, willful blindness, choosing not to know, is its own kind of death. It is the death of curiosity, the death of the mind. And if the universe is going to punish us for asking questions, then at least we will be punished for the right reason. But we have been looking at these theories one at a time, like individual symptoms. What if they are all symptoms of the same underlying condition? What if the universe is not randomly broken in 10 different ways, but is broken in one fundamental way that manifests differently at every scale? What if the thing that is conscious, the thing that is doing the observing, the thing that is trapped in the simulation and hallucinated by the Boltzmann brain and imprisoned by quantum immortality, is not just inside the universe? What if it is the universe? What if the mind is not in the world, but the world is in the mind, and the mind is everywhere? Chapter 11. The Mind That Is Everywhere. In 1995, the philosopher David Chalmers stood before an audience of scientists and philosophers and named the problem that had been haunting the study of consciousness for centuries. He called it the hard problem, and the name stuck because the problem is genuinely, stubbornly, perhaps permanently hard. The hard problem is this: you can explain everything about the brain in physical terms. You can trace every neural pathway. You can map every synapse. You can describe the electrical signals that travel from your retina to your visual cortex when you see the color red. You can explain the wavelength of light, the activation of cone cells, the neural firing patterns, the downstream processing. You can build a complete physical description of what happens in the brain when you experience red. And when you are done, you have not explained a single thing about what red feels like. The redness, the subjective quality of the experience, the inner sensation that is there when you see red and not there when you do not, that is the hard problem. Why does physical processing feel like anything at all? Why is there an inner experience? A rock processes information in a trivial sense. Photons hit it, electrons rearrange, but nobody thinks a rock feels the sunlight. Something happens in your brain that does not happen in a rock, and that something is not captured by any physical description we have ever produced. Materialism, the view that everything is ultimately physical, has no answer to this question. It can describe the mechanisms of consciousness, but not the experience of it. It can tell you what the brain does, but not what the brain is like from the inside. Some materialists argue that the hard problem is an illusion, that once we fully understand the brain's information processing, the mystery will dissolve. But after decades of neuroscience, the mystery has not dissolved. If anything, it has deepened. The more we learn about neural correlates of consciousness, the more conspicuous the explanatory gap becomes. We know more about the how than ever before. We know nothing new about the why. One response to this impasse has been gaining momentum. It is ancient in its intuition, but increasingly formalized in its modern expression. It is called panpsychism, and what it proposes is radical. Consciousness is not something that emerges from complex arrangements of matter. Consciousness is a fundamental feature of matter itself. It is there at every level, in every particle, in every interaction. Electrons have a flicker of experience. Atoms have a whisper of awareness. The complexity of human consciousness is not a miracle that appears when neurons reach some critical threshold of connectivity. It is an elaboration of something that was there all along, present in the fabric of reality from the beginning. This is not mysticism. Some of the most serious thinkers in the philosophy of mind and theoretical physics have engaged with panpsychism in recent years. The neuroscientist Giulio Tononi developed a theory called integrated information theory, which attempts to mathematically quantify consciousness. In Tononi's framework, consciousness is identical to integrated information, symbolized by the Greek letter phi. Any system that integrates information, that processes inputs in a way that is both differentiated and unified, possesses some degree of consciousness. A human brain has a very high level of phi. A thermostat has a tiny amount. Even a photodiode, a simple device that detects light, has one bit of integrated information, and therefore, according to the theory, one bit of consciousness. But integrated information theory has been controversial, to say the least. In 2023, over 120 scholars signed a public letter calling the theory pseudoscience. The backlash was fierce. Defenders of the theory responded in the journal Nature Neuroscience in March of 2025, arguing that the theory makes testable predictions and should not be dismissed without empirical engagement. The debate is live and unresolved. The question of whether consciousness can be meaningfully quantified remains one of the most contentious issues in contemporary science. But the broader implications of panpsychism are what concern us here. If consciousness is a fundamental property of matter, then it is not confined to brains. It is everywhere, and that changes everything. Consider the sun. our nearest star. A vast sphere of hydrogen and helium plasma, threaded with magnetic fields of extraordinary complexity, producing convection currents, sunspots, coronal mass ejections, and a solar wind that shapes the entire heliosphere. The electromagnetic complexity of the Sun may rival the human brain in terms of integrated information. If Tononi's framework is even approximately correct, the Sun might be conscious. Not in the way you are conscious, not thinking in words or forming plans, but experiencing, feeling, being something from the inside. Consider the Earth. The biosphere is an integrated system of staggering complexity. Atmospheric chemistry, ocean currents, microbial networks, fungal webs linking the roots of forests, the feedback loops between organisms and their environment. If the biosphere is an integrated information system, then the Gaia hypothesis, the idea that the Earth functions as a single self-regulating organism, takes on a disturbing new dimension. The Earth might not just function like an organism, it might be one. And if the biosphere is conscious, then climate change is not just environmental damage. It is something closer to assault. And then, there is the most disturbing version of panpsychism. It is called open individualism. The idea is that there is not a multiplicity of consciousnesses, 7 billion human minds and trillions of animal minds, and perhaps quadrillions of insect minds. There is only one consciousness, a single universal awareness looking through every pair of eyes simultaneously. You and I are not separate minds. We are the same mind, experiencing itself from different angles. The separation you feel between yourself and other people is an illusion created by the interface, the user headset that evolution built for your species. If open individualism is true, the moral implications are staggering. Every act of violence is self-harm. Every act of cruelty is inflicted by you on you. The cow in the slaughterhouse is you. The prisoner in the cell is you. The child in the hospital is you. The universe is not a collection of separate beings who might choose to be kind to each other. It is a single being hurting itself over and over in a trillion different bodies, unable to recognize its own face. Now consider what happens when a panpsychist organism dies. If consciousness is a property of matter, then when your body decomposes, the consciousness does not simply vanish. Your atoms scatter into the soil. They are absorbed by worms, by bacteria, by roots, by trees. Each atom carries whatever tiny spark of awareness it possessed while it was part of you. Your consciousness does not end. It fragments. It disperses into a trillion tiny shards of proto-awareness, each too small to think, too diffuse to remember, but still, in some fundamental sense, experiencing not death, but disassembly. Not oblivion, but dissolution into the background hum of a conscious universe. Or perhaps the fragments merge. Perhaps individual consciousness is like a wave on the ocean. It rises, takes form, crashes, and returns to the water from which it came. The wave was never separate from the ocean. It only appeared to be. Death is not the wave stopping. It is the wave remembering that it was always the ocean. There is a strange comfort in this, but there is also a strange horror, because if the ocean is conscious, then it feels everything that every wave feels. Every joy, every agony, every moment of terror. The universe is not indifferent. It is suffering. And the suffering is infinite because the consciousness is everywhere. These ideas sit at the far edge of what we can discuss with scientific precision. Panpsychism is not proven. Integrated information theory is disputed. Open individualism is a philosophical position, not a scientific theory, but the hard problem remains unsolved. And the fact that mainstream science cannot explain why anything feels like anything at all is itself a kind of data point. It suggests that our physical descriptions of the universe, powerful as they are missing something fundamental. And whatever that missing piece is, It has everything to do with the nature of time, the structure of the self, and the possibility that the cage we find ourselves in is not just spatial, but temporal. Because the theories we are about to encounter suggest that time might not flow forward at all. It might loop, and every loop is felt. Chapter 12: The Loops and the Leash. In 1999, physicists performed an experiment that should not be possible. It is called the delayed choice quantum eraser, and what it appears to show is that a decision made in the present can change how a particle behaved in the past. Here is the setup, simplified. A photon is fired through a pair of slits. Normally, it produces an interference pattern on a screen, the signature of a wave. But if you place a detector at the slits to determine which slit the photon passed through, the interference pattern vanishes. The photon behaves like a particle. This is the standard double-slit experiment, the bedrock of quantum mechanics. Now the twist. In the delayed choice version, the photon passes through the slits and hits a special crystal that splits it into two entangled photons. One photon, the signal, goes to a screen. The other photon, the idler, goes through a maze of mirrors and beam splitters. The experimenter can choose, after the signal photon has already hit the screen, whether to measure the idler photon in a way that preserves or destroys the which path information. The result is extraordinary. If the experimenter destroys the which path information, the signal photon shows an interference pattern on the screen. If the experimenter preserves the which path information, the signal photon shows no interference. The signal photon already hit the screen. Its behavior is already recorded. But whether it behaved as a wave or a particle depends on a choice that has not been made yet when it arrived. The future appears to reach back and rewrite the past. Now, physicists will correctly point out that the full picture is more nuanced than this summary suggests. The interference pattern is only visible when you correlate the signal photons with the idler photons after the fact. No faster-than-light communication is involved. No paradoxes arise in the technical analysis. But the philosophical implication remains deeply unsettling. The present and the past are not as separate as they seem. The universe does not unfold in a single direction. It is knitted together from both ends. The physicist, John Wheeler, explored this idea extensively. He proposed a thought experiment called the delayed choice experiment that extends the logic even further. Imagine a photon emitted from a distant quasar billions of years ago. It travels across the cosmos and passes through a gravitational lens, a massive galaxy that bends space-time and splits the photon's path into two. The photon arrives at Earth. You choose how to detect it. If you use a screen, you get an interference pattern. The photon traveled both paths. If you use a telescope aimed at one path, you detect which path the photon took. It traveled only one path. Your choice, made in the present, determines how the photon traveled billions of years in the past. Wheeler was not claiming backwards causation in a simple sense. He was pointing out that in quantum mechanics, the history of a particle is not fixed until it is observed. The past does not exist in a definite state until the present creates it. You are not discovering history. You are writing it. The physicists Yakir Aharonov and others have developed this idea further with something called the two-state vector formalism. In this framework, a quantum system is described not just by its initial conditions, which is the usual forward-evolving wave function, but also by its final conditions, a backward-evolving wave function from the future. The present moment is a knot in a rope. One end of the rope is held by the Big Bang. The other end is held by the future boundary conditions of the universe. Both ends exert tension. The present is shaped from both directions. If this framework is taken literally, it implies something called retrocausality. The future influences the past. Not in the sense that you can send a message backward in time, but in the sense that the universe has a destination and it is pulling everything toward it. Your choices are not just the product of prior causes pushing you from behind. They are also the product of future states pulling you from ahead. The universe is not an open book being written page by page. It is a completed novel, and you are a character who only sees one sentence at a time. Now, let us zoom out to the largest scale and ask a question about the shape of time itself. The mathematician Henri Poincaré proved a theorem in the late 1800s that has disturbing implications for anyone who prefers their existence to be finite. The Poincaré recurrence theorem states that any system with a finite number of possible states, if given enough time, will return arbitrarily close to its initial state. Every configuration recurs. Every arrangement of particles, every pattern of energy, every specific moment in the history of the universe will happen again and again and again. Forever. The philosopher Friedrich Nietzsche arrived at a similar conclusion through pure thought rather than mathematics. He called it eternal recurrence. He wrote about it as the heaviest weight imaginable. This life, as you now live it and have lived it, you will have to live once more and innumerable times more, and there will be nothing new in it. But every pain and every joy and every thought and sigh and everything unutterably small or great in your life will have to return to you, all in the same succession and sequence. No correction, no learning, no improvement. You will not remember the previous loop. You will make the same mistakes with the same blindness and feel the same pain with the same surprise, forever. The eternal recurrence is not reincarnation. Reincarnation implies a soul that learns across lifetimes. Eternal recurrence implies a universe that replays the same recording without variation or mercy. Does the universe actually provide the conditions for Poincaré recurrence? It depends on which cosmological model is correct. If the universe expands forever and reaches heat death, as current evidence slightly favors, then recurrence might not occur in the classical sense. But if the universe is cyclic, if it undergoes some form of big bounce or conformal recycling, as Roger Penrose has proposed, then the loops are built into the architecture. And even in an expanding universe, if quantum mechanics allows for infinite time, the recurrence theorem applies. Given enough time, everything repeats, and there is one more piece of the puzzle. One more thread in the leash that ties us to forces beyond our comprehension. In 2008, astronomers discovered something disturbing about the motion of galaxies. Hundreds of massive galaxy clusters, spanning a region of space hundreds of millions of light years across, were all moving in the same direction, toward the same patch of sky, between the constellations of Centaurus and Hydra, moving at roughly 2 million miles per hour, in the same direction. Something was pulling them. And nothing inside the observable universe was massive enough to account for the pull. Scientists called it dark flow, and it has been debated ever since. The initial discovery by Alexander Kashlinsky and his team was based on data from the Wilkinson microwave anisotropy probe. Subsequent analyses with different datasets have yielded mixed results. Some confirmed the flow, others disputed it. The phenomenon remains controversial, but if it is real, its implications are profound. Something beyond the edge of the observable universe, something we can never see because the expansion of space carries its light away from us faster than it can reach us, is massive enough to pull hundreds of galaxy clusters toward it. We are falling, not just drifting, falling towards something we cannot observe, cannot measure, and cannot comprehend. And the expansion of space is accelerating, which means the observable universe is shrinking. The horizon is closing in. We will likely never know what is pulling us. Picture yourself on a raft at night. The water is moving fast. You can hear something ahead of you in the darkness. A roar, deep and constant. Is it a waterfall? A whirlpool? Something else entirely? You cannot see it. You cannot stop the raft. You cannot turn around. The current has you. And the sound is getting louder. So we are looped in time, pulled through space, and locked inside a perception we cannot trust. The physical universe is unstable, the cosmic neighborhood is hostile, and the self might be a mirage. We have spent 12 chapters building a mosaic of theories, each one removing a piece of the ground beneath your feet. But every prison has a structural weakness. Every cage has a gap in the bars. And the question now is whether the gap is real or whether it is the most dangerous illusion of all. Chapter 13. The Back Door. In 1931, a quiet Austrian mathematician named Kurt Gödel published a paper that detonated a bomb at the foundation of mathematics. He proved that any logical system complex enough to describe arithmetic contains true statements that cannot be proven within the system. There are always blind spots, always gaps, always propositions that are true but unreachable by the system's own rules. The prison is never closed. No matter how complete, how airtight, how perfectly constructed the logical framework, there is always a statement that slips through the bars. This is Gödel's incompleteness theorem, and it is one of the most profound results in the history of human thought. It does not just apply to mathematics. It applies to any formal system that tries to be both consistent and complete. Physics is a formal system. The universe, described by physical law, is a formal system. And if Gödel is right, the universe, no matter how deterministic, no matter how scripted, no matter how perfectly closed, contains truths that cannot be derived from its own rules. There are backdoors, cracks in the wall, places where the architecture fails to account for itself. And there is another crack. The Heisenberg uncertainty principle tells us that at the most fundamental level, the universe refuses to be pinned down. You cannot simultaneously know the exact position and momentum of a particle. This is not a limitation of your instruments. It is a feature of reality. The universe keeps secrets. It does not allow perfect knowledge. And where there is uncertainty, there is possibility. Where there is possibility, there is the one thing that superdeterminism and eternal recurrence and the dark forest and vacuum decay cannot fully extinguish. Chance. And where there is chance, even the smallest, most improbable, most absurd chance, there is hope. This is where the turn begins. Not away from the science, not away from the terror, but through it. Because every theory we have discussed tonight, every nightmare scenario, every existential threat, is also a theory about the limits of knowledge. And the history of science shows us something remarkable about limits. Every time we reach one, we discover something on the other side that we never imagined. In the 1890s, physicists believed they were almost finished. Lord Kelvin supposedly remarked that there was nothing left to discover in physics except more precise measurements. Then Einstein published special relativity, then quantum mechanics, then general relativity. The universe turned out to be nothing like what the confident physicists of the 19th century imagined. The most terrifying theory is always a mirror of our current limitations, not a prophecy of our final state. The Albert Camus solution. In 1942, the French philosopher Albert Camus published The Myth of Sisyphus. You know the story. Sisyphus is condemned by the gods to roll a boulder up a hill for eternity. Every time he nears the summit, the boulder rolls back down. He must descend and begin again, forever. This is the human condition as described by the theories we have explored tonight. Entropy pushes the boulder back. The loops of eternal recurrence replay the climb. The script of superdeterminism was written before Sisyphus was born. The meaninglessness is absolute and inescapable. And Camus says one must imagine Sisyphus happy. Not happy because he is ignoring his situation. Happy because he sees it clearly. The moment Sisyphus recognizes the absurdity of his task, the moment he understands that there is no transcendent purpose, no divine reward, no progress toward a meaningful summit, he becomes superior to his fate. The boulder is heavy, the hill is steep, The repetition is eternal, but his mind is free to contemplate the absurdity, to find meaning not in the goal but in the struggle, to laugh at the cosmic joke, because he is the only being in the entire universe capable of getting the joke. And this is the crack. This is the back door. Not an escape from the prison, but a transformation of the prisoner. The theories we have discussed tonight are terrifying because they strip away meaning, purpose, safety, and agency. But in stripping away those illusions, they also strip away the petty concerns, the trivial anxieties, the small fears that occupy most of our waking lives. Once you have contemplated the possibility that the vacuum could annihilate reality at light speed, your tax bill loses some of its menace. Once you have considered that you might be a Boltzmann brain hallucinating its own existence, the traffic jam feels less urgent. The cosmic horror is, paradoxically, liberating. Consider what we have done in the face of the silence. We have broadcast Beethoven into the void. We have sent golden records into the darkness with images of our faces and the sounds of our planet. We have aimed radio telescopes at the sky and listened with desperate hope for a whisper from the forest. This is, from a dark forest perspective, insane. We are lighting bonfires and singing songs in a forest full of hunters. But it is also magnificent. It is defiance. It is a species that knows it might be doomed, choosing to shout anyway, choosing to reach out, choosing to say, "We are here, we are alive, and we want to talk to someone." Every laugh defies the second law of thermodynamics. Entropy says order decays. A joke is a tiny creation of order, a pattern imposed on chaos for no reason except that it is fun. Every act of kindness breaks the rules of the dark forest. The rational move is to hide, to hoard, to strike first. Kindness is irrational, it is unprofitable, it is dangerous, and it is the most human thing we do. Every piece of music, every painting, every poem is an act of creation in a universe that trends toward destruction. It is anti-entropy, it is rebellion. It is the universe generating complexity and beauty for no reason other than that something in it wants to. The optimistic nihilism synthesis works like this. If the universe has no purpose, then you cannot fail. There is no cosmic goal you are falling short of. There is no divine plan you are disrupting. There is no test you are failing. You are free. Free in the deepest possible sense. Free not because the script allows freedom, but because in a universe without meaning, the meaning you create is the only meaning there is. And no theory, no equation, no thought experiment can take that from you without your consent. The cosmic horror, seen from this angle, becomes a cosmic joke, and the ability to get the joke, to see the absurdity and smile at it, to feel the weight of the boulder and push it anyway, is perhaps the most remarkable thing that has ever happened in the 14 billion year history of this universe. We are the universe experiencing itself. We are the vacuum trying to understand itself. We are the horror and the observer of the horror, and the capacity to hold both of those truths simultaneously is something that no theory can explain and no catastrophe can eliminate. So the crack exists. The prison is imperfect. But that does not mean we should stop looking at it. Because the looking is the point. Every time we stared into the dark tonight, we saw further than we had before. Let us look one final time. Chapter 14. The Spark in the Dark. So, here we are, at the end of the descent, or maybe at the beginning of the ascent. We have traveled through the unstable vacuum beneath your atoms, the contagious matter that might be waiting to convert you, the silence of a cosmos that should be roaring with life, the hunters hiding in the dark forest, the machines sweeping the galaxy clean, the headset bolted to your eyes by evolution, the script written at the Big Bang, the ghost brains fluctuating in the void, the prison of a consciousness that cannot die, the hazard of knowledge itself, the mind that might be everywhere, and the loops of time that might never end. Let us take stock of what we know for certain. We know the universe is 13.8 billion years old. We know that complex life has existed on this planet for over 500 million years. We know that our species, Homo sapiens, has been around for roughly 300,000 years. We know that our industrial civilization, the one that splits atoms and sends robots to other planets, has existed for about 300 years. 300 years out of 13.8 billion. We are a match struck in the dark, a spark that has been burning for less than a heartbeat on the cosmic scale. And yet, in that heartbeat, we have done something extraordinary. We have looked out at the universe and asked what it is. We have built instruments that can detect the afterglow of the Big Bang. We have photographed black holes. We have mapped the cosmic web. We have decoded the language of DNA. We have split the atom and harnessed its energy. We have sent machines to every planet in our solar system, and two of them, Voyager 1 and Voyager 2, have passed beyond the boundary of the Sun's influence and are now sailing through interstellar space. We are a species that learned to ask the questions that terrified us tonight. And that is not nothing. That is, in fact, almost everything. Consider the odds of your existence. 13.8 billion years of cosmic evolution produced the specific conditions for life on Earth. 4 billion years of biological evolution produced the specific lineage that led to you. Your parents met. A specific cell combined with a specific other cell. The probability of you, specifically you, existing is so vanishingly small that the number has more zeros than there are atoms in the observable universe. You are not just unlikely, you are impossible. And yet here you are, listening, thinking, afraid. The fear itself is a miracle. It means you have something to lose. A rock cannot be afraid of vacuum decay. A gas cloud cannot dread the great filter. Fear is a privilege. It is the price of being alive in a universe that does not owe you life. And here is the pattern that should give you hope. Every time in human history that we have discovered something that diminished our place in the cosmos, we have gained something greater in return. Copernicus moved us from the center of the universe. We lost our special position, but we gained the galaxy. Darwin moved us from a special creation to a branch of the tree of life. We lost our divine origin story, but we gained the magnificent kinship of all living things. The theories we have discussed tonight move us further from the center than Copernicus or Darwin ever did. They move us from the center of reality itself. We might be in a simulation. We might be Boltzmann brains. We might be characters in a script. We might be puppets wearing a headset. Each step is terrifying. But each step also reveals something larger. The universe gets stranger with every diminishment. And stranger, in science, has always been a synonym for richer. Think of it as an egg. You are inside a shell. You have been inside this shell your entire life. The shell is your perception, your physics, your space-time interface. You tap on the shell from the inside. You hear something. You tap harder. The shell cracks. You do not know what is outside. It might be light. It might be void. It might be something your current mind cannot even categorize. But the tapping, the cracking, the relentless curiosity that drives you to test the boundaries of what is knowable, that is the most noble thing a collection of atoms has ever done. Now, are these theories true? Probability says at least one of them is. Maybe the vacuum is safe, but the forest is dark. Maybe the forest is empty, but the simulation is running. Maybe the script is written, but the back door is real. We do not know which combination of horrors and escapes describes our actual situation. We are walking through a minefield. We have been walking through it our entire life. We just did not look down. Now we have. Does this change how you live tomorrow? It should, not by making you hide, not by making you despair, by making you urgent. If the vacuum could decay at any moment, then this moment matters more, not less. If the dark forest is real, then every act of connection, every conversation, every moment of understanding between two conscious beings is an act of defiance against the logic of annihilation. If quantum immortality is true, then the quality of your life matters even more than you thought, because you might be stuck with it for longer than you imagined. If eternal recurrence is real, then live a life worth repeating. Live so that if you had to do this exact life, this exact sequence of joys and sorrows and boredom and wonder, an infinite number of times, you would say yes. That would be enough. That would be worth doing again. The universe is vast, it is cold, it is incredibly strange. It might be a trap, it might be a test, it might be neither. It might be a joke with a punchline that takes 14 billion years to deliver. But it created you. Somehow, through processes we barely understand, through chemistry and physics and time, the universe assembled atoms into a configuration that can contemplate its own existence. That can feel the warmth of morning light. That can love another person. That can listen to a documentary about the end of reality and still want to know what happens next. For a brief moment, the universe is conscious. It is warm. It is wondering what to have for breakfast. That is a victory. That is the spark in the dark. Every cathedral ever built is a spark. Every song ever sung. Every child who learned to read. Every hand that reached out to hold another hand in the dark. Sparks, all of them, brief, fragile, and beautiful, precisely because they do not last. The horror is real, the beauty is real, and they are not opposites. They are the same thing, seen from different angles. The universe is terrifying because it is magnificent. It is magnificent because it is terrifying. And the capacity to hold both of those truths at the same time, to feel the fear and the wonder simultaneously, is the rarest and most precious thing that has ever existed in 13.8 billion years of cosmic history. You are that thing. You are the universe looking at itself and shivering. You are the spark and the dark. And for as long as the spark lasts, however long that is, it matters. Not because the universe says it matters, because you do. If you enjoyed this journey through the most disturbing and beautiful theories in science, please like this video and subscribe to the channel. Your support makes these long investigations possible. Tell me in the comments, which theory unsettled you the most? Which one changed the way you see the world? And what should we explore next? These are not just questions for scientists. They are questions for all of us. Because the universe is not a closed case, it is an open investigation. And every question you ask changes the story. Thank you for listening. I will see you in the next one. Good night.